Imagine you're standing outside on a clear starry night. You look up and see countless stars scattered across the sky, each twinkling like a beacon from some far-off world. It's breathtaking, right? But have you ever stopped to wonder, why does anything exist at all? Why not just nothing? The universe had a beginning, but how could scientists confirm that this Big Bang really happened? How did this explosion give rise to the intricate universe we observe today? The deeper you think, the stranger it gets. The laws of physics as we understand them seem to treat matter and antimatter equally. And yet, when we look out into the universe, everything we see, the stars, the planets, even ourselves, is made of matter. Where did all the antimatter go? What cosmic forces decided that matter should win the grand battle of existence? These questions have puzzled scientists and philosophers for centuries, driving them to explore the universe's most profound mysteries. For centuries, the universe was thought to be eternal and unchanging. Many ancient cultures believed that it had always been here, a static canvas painted with stars. This notion held sway for a long time until, in 1927, a Belgian priest and scientist named Georges Lemaitre proposed something revolutionary. He suggested that the universe had a beginning, a starting point he called the primeval atom. According to Lemaitre, the entire universe originated from this incredibly dense point, which then exploded and expanded into the cosmos we see today. This idea was groundbreaking and, at first, not widely accepted. The universe having a beginning sounded almost mystical, and scientists of the time were hesitant. But then, in 1929, astronomer Edwin Hubble made a startling discovery. The universe is expanding. Galaxies were racing away from each other as if they had all been pushed apart by a tremendous force. This observation supported Lemaitre's idea and led scientists to reconsider how the universe came to be. Imagine rewinding the universe's history like a cosmic videotape. The galaxies would rush back toward a single, incredibly dense point. This concept was initially ridiculed by some, including astronomer Fred Hoyle, who mockingly called it the Big Bang Theory. Ironically, the name stuck, and it has since become one of the most well-known theories in science. But how could scientists confirm that this Big Bang really happened? Enter Ralph Alpher, George Gamow, and Robert Herman. They made a bold prediction. If the universe began with a massive explosion, then a faint afterglow, an echo of that colossal event, should still be detectable throughout the cosmos. They called it the cosmic microwave background radiation. Years passed, and this prediction remained just a theory until the 1960s when astronomers Arno Penzias and Robert Wilson stumbled upon something extraordinary. They were trying to tune into microwave signals from our Milky Way but kept picking up a mysterious noise. No matter where they pointed their equipment, the noise persisted. Little did they know they had accidentally detected the cosmic microwave background radiation, the very afterglow of the Big Bang itself. This was the smoking gun that confirmed our universe had a fiery beginning, the birth of everything. So, how did this explosion give rise to the intricate universe we observe today? Let's take a journey back to approximately 13.8 billion years ago, to the moment of the Big Bang. All the matter in the universe erupted from an infinitely small, impossibly dense point called a singularity. In a violent explosion, space itself began to expand. And here's the crazy part, it wasn't just expanding, it was inflating. Within a fraction of a second, the universe doubled in size every tiny sliver of time, so fast that it's mind-boggling to imagine. During this initial phase, gravity and other fundamental forces of nature began to take shape. Energy condensed into particles, forming both matter and antimatter. But there was a twist. For reasons not yet fully understood, there was a tiny imbalance. For every billion particles of antimatter, there were 1,000,001,001 particles of matter. As matter and antimatter collided, they annihilated each other, releasing bursts of energy. But because there was just a bit more matter than antimatter, some of it survived, and this leftover matter would eventually form everything we know: stars, planets, galaxies, and even us. Within the first few seconds of this cosmic fireworks show, protons and neutrons formed. Shortly afterward, these particles began to fuse, creating the nuclei of hydrogen and helium. But it would take around 300,000 years before things cooled down enough for atoms to form. This cooling allowed nuclei to capture electrons, creating stable atoms of hydrogen and helium gas that filled the universe. The era of light had begun, as atoms could now release photons without being immediately absorbed. But the universe wasn't done evolving. About 380,000 years after the Big Bang, the cosmic microwave background radiation, the afterglow detected by Penzias and Wilson, began to spread throughout the cosmos. This light carried with it minuscule fluctuations in density, tiny ripples that were stretched to cosmic scales by the rapid expansion of the universe. These ripples would become the seeds for the formation of galaxies, stars, and all the cosmic structures we see today. Now let's fast forward a bit. Over millions of years, gravity worked its magic. It pulled together clouds of hydrogen and helium gas, compressing them until they ignited to form the first stars. These stars were like cosmic factories, fusing hydrogen into helium and other heavier elements in their fiery cores. When they exhausted their fuel, they exploded in spectacular supernovae, scattering these elements across space. This debris gave rise to new generations of stars, and around some of these stars, planets began to form. Our own solar system is a product of this cosmic recycling process. The iron in your blood, the calcium in your bones, the oxygen you breathe, all forged in the hearts of ancient stars that lived and died billions of years ago. But what about the universe's structure on a grand scale? Why do galaxies cluster together, and what holds them in place? This is where dark matter enters the story. Invisible and enigmatic, dark matter acts like a cosmic scaffolding. Without it, the universe's matter would have dispersed long ago. But dark matter's gravitational pull helped to gather normal matter into the galaxies and clusters we observe. Now, back to that earlier mystery, the asymmetry between matter and antimatter. In the beginning, they should have existed in equal amounts. So what tipped the balance, allowing matter to dominate? One leading hypothesis involves the idea that the universe, in its early moments, bent the rules of physics for a brief period. During this cosmic loophole, interactions occurred that favored the creation of matter over antimatter. Imagine a cosmic coin flip that, against all odds, kept landing on heads just enough times to give matter a slight edge. And then there's dark matter. This invisible substance doesn't emit, absorb, or reflect light, making it incredibly hard to detect. Yet it's crucial for holding galaxies together. Scientists have proposed many theories about its origin. It might be a relic from the hot, dense phase of the early universe, or it could have formed during phase transitions as the universe cooled. Some even suggest it's a new kind of neutrino or a result of gravity giving rise to exceptionally heavy particles. Why is there something instead of nothing? Could the universe have sprung from nothing? It seems counterintuitive, but quantum theory offers a fascinating possibility. According to this theory, the very fabric of space can experience random fluctuations, which might spontaneously generate particles out of a vacuum. Some scientists speculate that a tiny bubble of true vacuum could expand rapidly, triggering a Big Bang-like event. This isn't just wild speculation. Recent breakthroughs by physicist Dong-Gang Wang and his team have provided mathematical support for this idea. Then there's the eerie universe theory, which suggests our universe is just one in a series of cosmic cycles. Imagine two higher-dimensional brains colliding, sparking off enough energy to create everything we see. This theory hints at the possibility of a never-ending cycle of universes, an eternal cosmic dance. As we piece together the universe's story, we encounter profound questions that push the limits of our understanding. Dark matter, cosmic inflation, quantum fluctuations. Each offers tantalizing clues about how our universe came to be, yet they also reveal how much we still don't know. The very concept of nothingness challenges us. Can we ever truly grasp a state where space, time, and physical laws simply don't exist? Despite these mysteries, our exploration continues. Each discovery is a step toward understanding the cosmos's intricate tapestry, where chaos and order coexist to create the universe's wonders. It's a journey that not only expands our knowledge but also reminds us of our place in the grand cosmic drama. So, as you look up at the stars tonight, remember, we're all part of a story that began billions of years ago. A story of explosive beginnings, cosmic cycles, and the enduring mysteries of existence. Thanks for joining me on this journey through the universe's origins. If you're curious to dive deeper into these concepts, be sure to check out my next video on cosmic inflation, the rapid expansion that set the stage for everything. Until then, stay curious and keep exploring the wonders of the universe.